What's oh, okay, it has started. Okay, so now let's see. So again, you have this thing that it is a polynomial of degree n, number of vertices, leading term k raised to the power n, constant term 0, they alternate in sign, and also you have this thing that the coefficient of k raised to n minus 1 is minus epsilon, minus the number of edges. We always start with simple graphs, but we can have non-simple graphs while working, okay? Now we'll see something, okay? But first of all, let's see examples of computation. They suggest two different possibilities. I always prefer the first one, which is go down up to the empty graph, okay, or something of which you know anyway the chromatic polynomial, okay. Let's see these computations. So you start with this, and then on one side you erase, on the other you contract, and don't forget the minus sign in front of what you contract. So you have this, okay? And what about this? This splits into, you pick up this edge, delete, and contract. This, with your minus in front, becomes here you delete and here you contract, and so minus and minus will be plus, okay? And here what do? You delete, okay, on one side, and on the other side you contract, but if you contract this you just get three isolated vertices, okay? Here you delete and you get 3 isolated vertices, or you contract and you get 2 isolated vertices. Here you delete, and so you get 3 isolated vertices, the third one which you get with the minus sign, and contract and get 2 isolated vertices. Here you delete and get 2 isolated vertices, or contract and get 1 isolated vertex, okay? But here it's very easy in this case because you just get to the empty graphs, and so what you get is 4 isolated vertices, k to the 4th, minus 3 isolated vertices, and so on and so forth, okay? And then you can also gather everything like this. Or the other possibility, but I never use it, but it's still possible, when you already have quite a lot of edges inside the graph, maybe it's better to reach, on the other hand, to reach the complete graph on that number of vertices. But it's tricky because on one side you try to reach the complete graph, but on the other side you contract, and so on one side you grow things, on the other side you lower things. So I think it's much less comfortable. Okay. Anyway, it's always in the same way. You want to compute the chromatic polynomial of this, and so you have that it is chromatic polynomial of this plus chromatic polynomial of this, as we saw. You add that edge and contract that edge, and so on and so forth. Okay, and you get your polynomial. Okay. What to say? Well, here I suggest that these computing the chromatic polynomials of these is just using the recursive formulas we have seen. Showing this 842 is tricky. Don't think more than 10 minutes, and I never ask this at an exam. Okay. apart from no, not even for, no, I give honors, laude, for much less than this. So I think it's a very interesting problem, not terribly difficult, and very interesting, but don't spend more than 10 minutes. And I'm not going to prove it anyway, because I want to go on in the theory instead, and it is a nice exercise anyway. And above all, keep in mind that this is important. You must have this as the coefficient of k raised to n minus 1. If you don't get this, you are surely wrong, okay? Then I always use the chromatic polynomial of a tree instead of going up to the empty graph. I stop when I have a tree, because then I can use the chromatic polynomial of the tree with the number of vertices. And okay, if somebody remembers, I have very bad memory, and so I never remember the chromatic polynomial of a cycle. But if you are so good as to remember this, it's not a terrible formula, but if you can remember it, you can use it, okay? And okay, just let me give you this information, but it's nothing really important. In any coloring, the vertices in a clique must all be assigned different colors. So you might think that you have large cliques if you have a big chromatic number. It's not so, because for any positive integer k, there exists a k chromatic graph containing no triangle. So it is a strange part of the theory in which many things are not as you might imagine, okay, but nothing more than that. There is another here. Let me, a storage problem next Tuesday, okay, I'll talk about this. I want now to give you hints for the computation and an example of computation, okay, on the midterm that we had, okay? So, hints. Do you remember that I gave you some hints for simplifying the computation of the number of spanning trees? Okay, here things are different. Be careful, be very careful, okay? First thing, tricks. So, as I told you at the beginning, if you happen to have multiple edges, not at the beginning, but during your recursion, when you contract, you might get multiple edges, okay? Very easy. You have a certain behavior if you are computing the number of spanning trees. I'm not recalling that. But now, as I told you, being connected by 3, 2, or 1 edge is exactly the same thing. So you can substitute parallel edges with just one edge, okay, which is comfortable, okay? Other tricks. You land because you didn't do something before which could have helped you, but you land by contracting to a loop. We have seen that we can get loops when you do contractions, okay? Then this is 0 if you get to a loop.
Even if we had a big graph with just one loop?
Just one loop is enough for saying no. this part is 0. This will be a big part, a part of your recursion, okay? So one of the many graphs into which you are splitting everything, because you divide into 2, into 2, into 2, into 2, okay? And so one of these might have a loop. Then that part there has 0 as chromatic polynomial, okay? Then also,
any part with a loop has chromatic pi of 0.
sure, yeah. But generally, you don't reach that situation. But if you reach it because you didn't mind something before, then that part is 0. Okay. You have that by deleting an edge, you get to something which is disconnected. When it was for when we had to compute the number of spanning trees, that was 0, not here. Pi k of this equals pi k of this times pi k of this. Okay. Why? Because now, coloring of the two components is independent. For each coloring of this component, I have all possible colorings of this. For each coloring of this, I have all possible coloring of this, and so you have this product, okay? And now what? Okay, okay.
Color, right?
Pardon me?
You mean they can share color?
No, they can share color, and not only, but think. I have 6 color available, and I want to color this in all possible ways. Okay, color this part in one way. Here you can color this other part in all the possible ways of this. So you have that the number of colorings of this is the number of colorings of this times the number of colorings of this. Okay, exactly because of the meaning of pi k. Okay. And then there is something which was used again by some Iranians, and be careful. I think it was because they had it in some circuit exams before. Be very careful, but there is a possibility which is also present here, and it is this 8.4.7. This is tricky, tricky, tricky. Be very careful. You can use it. I suggest that you use it only in one very particular case, which is this. When you have a cut vertex, okay, pi k of this equals pi k of this times pi k of this divided by k. Okay, I suggest that you don't try to use it in more complicated situations. Okay, because I've seen many students using that particular theorem that here appears as an exercise, but in a wrong way. Okay, so just use it for when you have a cut vertex. Okay. When we had cut vertex for the computation of tau, we just had the product of the two parts. Here we have the product divided by k, which is the chromatic polynomial of this vertex by itself. Okay? If you want simply product, you must have two different components. Okay, so now I would like to do the computation for what we have in the example, which was this, okay? It would be terribly. Okay. So here we must keep track of. No. Okay, on one side I delete that edge. On the other side I contract that edge. And when I contract, I have a minus sign. Okay, so here I delete and contract. I delete and contract. Here you see I contract and I get multiple edges, but then I say no problem, this will be equal to this. Okay? And I'm already done, because when I reach trees, I know how to put things, to have their polynomials. Let's not forget the minus sign here. This is the nasty one. Let's go on with this. So I'll keep track of the minus, okay? So here on one side, I delete and I have a minus there, okay? On the other side, I contract but minus times minus, this is plus. Okay, and this again is what is equal to, sorry, here I want a minus, okay? And here I have a plus and it is like this, okay? Since I don't remember the chromatic polynomial of cycles, I still split, I'm sorry. And so I split here, and so I get that I delete, so minus, delete, and minus minus plus, and contract, which is equal to this, okay? And here, on one side, I delete, on the other side, here it's plus, and so on the other side with minus, I contract, which is minus this, okay? So now I use this for trees, okay? If I have a tree with knee vertices, its polynomial is k times k minus 1 raised to knee minus 1. So this is with 1, 2, 3, 4, 5 vertices. So this will be equal to k times k minus 1 raised to the 4th power. This will be minus, this is 4 vertices, and so it is k times k minus 1 to the 3rd. Okay, this is 4 vertices as well, so this is also minus k times k minus 1 to the 3rd. This is 3 vertices, so this is k, and with plus sign, k times k minus 1 to the second. And also this is k times k minus 1 to the second, and this is 2, and so it is minus k times k minus 1 to the first, okay? And so what I get is the sum of all these, which means what? So I get, let me write it down here. I get k times k minus 1 to the fourth, and I have 2 of these, minus 2 times k minus 1 to the third, plus 2 of these, 2 k minus 1 to the second, minus k times k minus 1. Okay, and I think I have the possibility of scrolling. Okay, not so much, because then what? Oh, let's add a page. What a silly thing. Okay, I'll take off this. Okay, I'll keep it like this. Oh, I don't like very much this.
Professor, sometimes these elements they cancel each other out.
No, please repeat.
Sometimes one of these elements they cancel each other out. For
Oh
example,
yeah, that's possible. Now you can do whatever you want.
I know,
Okay.
I know. I want to know about the meaning of this. Why? What happens when two of these cancel each other? What went wrong? What was the situation?
No, nothing wrong. Nothing
No,
wrong.
I know it's not wrong. I mean, for example, in an application, we are using this and we see that we made a contract and we canceled two things. What does it mean? It means that we have an extra vertices or we are.
No, I don't think so. I think that it's just the fact that you might get the same partial result on one side with plus and on the other side as minus, and not exactly the same, meaning isomorphic. Just a moment for that, but I must go on rapidly because we have another important thing to learn before Monday. So just rapidly here, for instance, look at here. Here you have something with, okay, here they came with the same sign, but it might very well happen that you get it with different signs, but they are different trees inside the original graph. But they are not even isomorphic. They are just trees with the same number of vertices, okay? And so you get here they sum, but you might get them erasing, canceling out, and I don't think it has a really deep meaning, apart from the fact that you have on one side a certain tree with 4 vertices, on the other side another tree with the same number of vertices. Okay, I don't know, combinatorial theory is very tricky, so it is possible that there is a deep meaning, but I'm sorry, I don't know it. But now I must really go on with these things.
That's all right. Thank you.
I'm very happy that you have curiosities like this, but I cannot help you in this moment. So here, very rapidly, I'll try to do this computation. So, Tartaglia or Pascal triangle, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Okay, so here I have k to the fourth, but multiplied by k, so k to the fifth minus 4 k to the fourth plus 6 k to the third minus 4 k to the second plus k, which is this first part, and then we have minus 2k this, okay? So this was done. So now minus 2 and the cube of k minus 1. So it will start with k to the fourth. 2k to the fourth minus 2. Be careful because I often take them wrong. Minus 2k to the fourth, and then I have plus 6k to the third minus 6k squared plus 2k. Okay, and this is done. Then I have k minus 1 squared, so plus 2, I start with plus 2k to the third, plus 2k to the third, minus 4k squared, plus 2k, and this is done, and then minus k squared plus k. So at the very end, we should have k to the fifth minus 6k to the fourth, 8, 9 plus 9k to the third, 10, 14, 15 minus 15k squared, 1, 5, 6 plus 6k. So let's see whether we have that at least our conditions are satisfied. Okay, how many vertices? 5. K to the fifth. Okay, how many edges? 1, 2, 3, 4, 5, 6. Okay, and actually we have minus 6 as the next. Then no constant term. Then alternating signs. And then there is also a thing which is still unknown, but always checked, that they raise in absolute value and then decrease. All chromatic polynomials seen so far in the world have this situation, but it has not been proved that it is always so, and no counterexample has been found. But still, I guess that it's good to see 1, 6, 9, 15, and then down 6, okay? You don't raise again and, okay. You raise up to a certain point and then go down in absolute value. So, as far as I can see, this could be, and if I'm wrong, I'll get 3 points instead of 4. Why? Because all the basic rules for chromatic polynomials are satisfied. So if you have at hand my solution, please have a look to see whether it is actually the true chromatic polynomial, which I checked that with the program for doing that. Okay, but please have a look. Is it the same? Is it correct? Has anybody solution at hand? No. Okay, I'm going to see.
It should be plus 14K, and the rest is correct.
So
it must be not 9 but 14K. The rest is correct.
This
should be 14.
14. How come? So in my notes, it's 14. So where was it wrong? Let's see what's wrong here. So, thank you. This is the easiest one. Okay, let's see here. Yeah, sure. Here it is. It is minus 2 times this times minus 3 times this. So this is plus 6. Yeah. And now it's all right. Thank you very much. So this is 14. Thanks a lot. So I had just 3 points instead of 4 in my in my midterm. Okay, it's exactly what I said. Okay, it can happen. Can you see very easily? But my mistake was not easy to check because it did not give me something not working in the sense they were alternating in sign, they were increasing and then decreasing in absolute value. So at the first sight, I had no possibility to check. But it's wrong, so 3 points instead of 4. Okay.
Sir, what was the name of this method to calculate this?
I don't think it has a name. It is recursive formula for the chromatic polynomial. Okay? Now, I want you to see that other thing which fills the last, yeah, we have time to do it. The last thing we are interested in for our midterm. First application, I don't. Okay, no, it's still here, but it's a part which, okay, let's see. As an application, you can have this, that you have and chemicals, and you have to store them, but there are incompatible ones, okay? So chemicals which have not to stay in the same room, so to say. So what's the least number of compartments? Now what can you do? You write down, you draw, if you want, a graph with as many vertices as chemicals, and then you join two vertices if the corresponding chemicals are incompatible, okay? And then you try to color the graph with the least possible number of colors. Why? Because when you have the vertices with one same color, you know that you can store them in the same compartment, okay? Why? Because they form an independent set, meaning mutually non-adjacent, which means mutually non-incompatible. So compatible, okay? And so you want to save the number of storage rooms, and that corresponds to the minimal number of the coloring, okay? All right. Now, how to try to give colors to a given graph. Here is, well, this is again a problem which is hard in terms of computational complexity. But there is here a procedure which is good, but not very efficient for large graphs, as they say. Okay, let's see how it works. The chromatic number of a graph is the least number of independent sets into which its vertex set can be. Okay, so what we can do is finding independent sets maximal independent sets, okay? And then what you do is to you determine the biggest independent set and give it a certain color. Then take that away, okay, and give and find the independent sets of what is remaining and give another color, and so on and so forth. Okay, but this is not what is of interest for our no, the goal they are expressing here is not the goal of what we are doing in the midterm. What we are doing is this. In order to find maximal independent sets, they look for their complements, which are minimal coverings. Okay. So what we are doing in the midterm is finding all minimal coverings and their complements, which are the maximal independent sets. Okay, that's all for us. They put it here because this is part of coloring a graph. Okay, but in this moment we are not interested in coloring. We are interested in this. I have a graph. I want to find all maximally independent sets. How do I do? By finding all minimal coverings. And now the interesting thing is that we use some logical operations. I know that some of you already know all this. Please forgive me if it is boring, but I think it's a nice thing to see the interplay of this type of problems with elementary logic. Okay, the idea is this. A procedure for finding minimal coverings. And it is a set of instructions which becomes a set of logical expressions. So you visit each vertex, and for each vertex, either you choose that vertex, or you choose all its neighbors. Okay? Otherwise, there will be at least one edge which has no ends in the covering. We are looking for covering. Okay? So if you sit in a vertex, two possibilities. Either you take this vertex, or you take all of its neighbors. Okay? If you don't do one of these two things, there surely will be one edge which is not covered. Okay? Okay, now, and visit the next one, and either choose it, or choose all of its neighbors, and so on and so forth. Now there is this thing that we can do some computation with the logical sum for either or, for the inclusive or, and the product for the and, okay, for the connective and. Okay, what is important here is that you have two very interesting simplifications, okay, of logical expressions. When you have that in a certain monomial, in a certain product, you have that the same element comes more than once, you can leave it just once, okay? Eliminate the doublings. And this is why, because A and A equals to A, okay? And if you have an OR in which you have that there is a monomial which is contained in another monomial, then the bigger one can be eliminated. So I'll write it down now. UV equals UV. Okay. This for why? Because actually what is important here is that V equals V, which means let's take the truth table. Okay, we have sorry. V, and V. This is and. Okay? And you have true and V again. True, false, and of course you must have true and false in the same positions. And so what you have is that the and gives you true if both are true, and gives you false if even just one of the two is false. And so the truth table of V and V is equal to the truth table of V. Okay? And then you have something like U plus UV equals U. Let's see why. Here we have U, V, UV, and U plus U, UV, which means UV, U and V, U or U and V, where this is or. Okay, so truth table, true, true, false, false, true, false, true, false, U and V, true, false, false, and false. And here you have U or U and V, and this is true if at least one of the two is true. Okay, so we have to check U and V. True and true, it is true. True and false, it is true. False and false, it is false. False and false, it is false. And so you see that the truth table of this is exactly as the truth table of U. So you have these two extra possibilities of simplifying, which in numbers, obviously, you do not have. Okay? But don't forget them. And now we see the computation for the usual graph. Okay? And so
sorry, bro. For applying this property, the two intells have to differ just for one.
No. If you have something which is contained in a bigger, you delete the bigger, whatever you have in the rest. Now you'll see now. You'll see now. Okay. So we have this. I don't know whether the numbering is the same, the names are the same as in the, okay, it's not important, C, D, E. Okay, so now what do? I visit A, and so I take either A or B and E. Okay, then I visit B, and either I take B or I take A, C, and E. Okay, now I visit C, and either I take C or I take B and D. Now I visit D, and either I take D or I take both C and E. Then I visit E, and either I take E or I take A and B and D, which are its neighbors. Okay? So now I start my computations. I start here, I have A, B plus A, C, E, okay, plus B, E, B plus B, E, A, C, E times all what remains. Now, simplifications. First simplification inside each monomial. Here I have a repetition. Away. Here I have a repetition. And here I have a repetition. Okay? So first I get rid of the repetition inside the monomials. Then let's look whether we have a monomial contained in another monomial. Yes, we have. BE is contained in BEAC. So I get rid of this. Do you prefer that? Maybe it's better that I do it in another color. Okay, do this. Okay, and then in yellow, I take away this, which is, okay. So this is like having, so this will be AB plus BE, oh, sorry, plus ACE plus BE times C plus BD times all the rest, which means ABC plus ABBD, sorry. Then plus ACEC plus ACEBD plus BEC plus BEBD times all the remaining things. So inside the monomials, this, and this, okay? No repetition inside the monomials. Now let's see, a monomial inside another, ABC is contained in ACEBD. We have the commutative property, okay? So ACEBD, it's the same as ABDEC and so on. So ACE is contained in, and also ABC in ACEBD. So I get rid of this. BEC, BED, no, nothing more. So this is equal to, our simplification now is ABC plus ABD plus ACE plus BEC plus BED times the next one, which is D plus CE times what remains, okay? Which means A, B, C, D plus A, B, C, C, E plus A, B, D, D plus A, B, D, C, E plus A, C, E, D plus A, C, E, C, E plus B, E, B, E, C, D plus B, E, C, C, E plus B, E, D, D plus B, E, D, C, E times what remains. Okay, so now let's see what we can do. Inside each we have here, we have a double C, here a double D, here C and D, here C and D, here a D, and now let's see whether we can find something inside something else. ABC inside ABCD. ABC inside also this. ACE inside ABCE. ACE inside ACED. BED inside BEDCE. BED inside BECD. And I think it's so. So now we have ABD plus ACE plus BEC plus BED times E plus ABD, which equals ABDE plus ABD, ABD plus ACEE plus ACEABD plus BECE plus BECABD plus BEDE plus BEDABD. So now ABD, easy. ACE, double E. ACE, ABD, I just can take away A, BECE, BECABD, I take away this B, BEDE, I take away an E, BEDAB, I take away B and D. And now I have ABD, which is inside ABDE. ACE, which is inside ACEBD. BEC, which is inside BECAD. BED, which is inside BEDA. Okay? And so I think now I'm done, because then this means that I have only ABD plus ACE plus BCE plus BDE. And that's all. And let's see Okay, how can I do? Or where can I put it? Maybe I can here, I hope so. Our graph is like this. And we have A, B, C, D, E. Now, please have a look whether this has a meaning. Okay, it is nothing meaningless. It must be, they must be coverings. And so, let's see, A, B, and D. If I take A, B, and D, is every edge covered? Yes. And is that a minimal covering? What if I take out B, for instance? If I just take A and D, there is this edge BE which is uncovered, okay? So this is actually a minimal covering. ACE, yeah, again, it is a minimal covering. BCE, B, C, and E, yeah. And BDE, also a minimal covering. So these are minimal coverings are A, B, and D. A, C, and D. B, C, B, C, and E. And B, D, and E, sorry. Maybe I can write down here. Oh, yeah, I can. So, out of minimal coverings, I can get maximal independent sets, which are the complements. ABD, I've left out C and E, C, E. ACE, and so I've left out B and D. BCE, and so I've left out A and D. BED, and so I have left out A and C. Just a moment for seeing whether it's okay. C and D are independent, and if I add any vertex, I get two which are adjacent. B and D independent, AD independent, AC independent. It's all right, okay? And so this is the answer. And with this, we know how to work out all the questions of the midterm, okay? And so, okay, if you have questions, please ask me by email. If you really need, we can also make an appointment for with Teams or yeah, Teams is all right. We have already our class for meeting. Okay, no problem. Many things can be solved by email. Otherwise, we'll find a moment for talking together if you need. Okay? And all right. Good luck for next Monday. 14 out of 24 for being admitted to the oral, and obviously it also has influence on the final score, but the important thing is passing or not passing, being or not being admitted to the oral. Tell me?
The length of my midterm term is 1 hour and 30 minutes. Maximum length of the midterm.
The period, you mean? Yeah, you have both hours, okay? So we'll start always at 10 past and 10 to, okay? Generally, I think almost everybody will be finished much long before. And so in the last half hour, I'm going to talk for the ones who have already finished, just to do something, since I'm paid for doing it, okay? And I think it's also interesting for you, and it will be something not in the program, because one must be allowed to go up to the end of the 2 hours for the midterm without listening to me, shutting me up without any problem, okay? All right. Then see you next time.
I think it is good to notify the people who are in remote that on Sunday there is a day saving time, so they change the time.
Oh, yeah. No, yes, very nice, very nice. Please. No, that's true. Very good thing that your fellow student here reminds you. In Italy, and I think in all of the European Union, we are changing from a summer legal hour to winter legal hour, which is actually the solar hour. So we are on Sunday morning, we are changing to what we are taking 1 hour less. So say your clock will show 10 o'clock, you must make it 9 o'clock, okay? I guess you'll wake up at 10 o'clock or so. Okay, so be careful about that for the time of next week. Thank you very much. You had also something to tell?
Not about A1, but about click and independent sets.
About independent sets?
Yes. Is it okay in our background that we, for example, we say that for independent sets definition, a subset that has no such that no vertices in the set are adjacent.
That no?
No, two.
No, two are adjacent. Yeah. This is the definition. Yes. Another way of seeing the independent sets is this. Take a graph. There is a notion which is the complementary graph, which is same vertices and the missing edges. Okay, so think of having your edges painted red. Okay, now you paint blue the edges which are missing if you want to do a complete graph with those vertices. Okay, now I'll do it. Okay. Okay, the lecture is over, but I answer an interesting question. So, example. Okay, I have. Oh, I've said that it did it no, I'll do it in black now, okay? And so I put this, okay? This is a certain graph, okay? What's the complementary graph? I'll put the, let me do this. Let's say that, okay. This is our graph, okay? Now what's the complementary graph? I put there in red, same vertices, and I put in red the missing edges which would build the complete graph. So our original graph is this. Okay. This is G, and we have I think it's this. Okay, this is GC, the complementary. Okay, I hope I did it well. Okay, so you know what a clique is. For instance, this here is a clique of 3. Okay, And independent sets of G are the cliques of G complementary. Okay? And so here, for instance, you have cliques of 2 in the complementary. Well, this is an independent set of this. This clique of 2 is an independent set. And so since you see here that there are no triangles, no cliques of 3, you know that you have at most 2 vertices in any independent set of G. So independent sets of G as cliques of the complementary graph. That's an interesting way of seeing things. Okay? Okay, now I close everything. Thank you for this very nice question.